Hello there and welcome to the Sleepy Science Channel. I'm really glad you found your way here tonight. Maybe it was a long day. Maybe your mind is still turning over things that don't need to be turned over anymore. Or maybe you're simply the kind of person who likes to fall asleep thinking about something real and vast and quietly astonishing. Either way, you're in exactly the right place. There's nothing you need to do right now, nowhere to be. Nothing left to solve tonight. Just let your body settle into wherever you are, let your breathing come a little more slowly, and let your eyes grow heavy. Because tonight, we're going to explore something that is above you right now, above every person and every city and every mountain on this planet, something you have lived inside your entire life without ever fully knowing it. Tonight, we're going to travel through Earth's atmosphere. Layer by layer, from the air you're breathing right now, up through the clouds, past the point where the sky turns from blue to black, through the shimmering auroras, and all the way to the very edge of space itself. Some of what you hear tonight will surprise you. Some of it will feel quietly beautiful. And some of it will remind you that this thin, invisible shell surrounding our planet is one of the most extraordinary structures in the known universe. And if these calm explorations help you rest a little easier, consider subscribing to the channel. It helps other people find their way here too, one sleepy soul at a time. Now let's begin. The atmosphere is thinner than you almost certainly imagine. We talk about the atmosphere as if it's a substantial thing, a deep ocean of air surrounding the planet. But compared to the size of Earth itself, it is remarkably, almost unsettlingly thin. If you were to shrink Earth down to the size of a standard classroom globe, the atmosphere that supports all life, filters radiation, drives weather, and makes the sky blue would be no thicker than a single coat of varnish on that globe's surface. The vast majority of the atmosphere's mass is compressed into the lowest 15 kilometers. Roughly 99% of all the air on Earth sits below that altitude. Everything above is increasingly thin, increasingly cold, increasingly close to the silence of space. The sky may look deep and blue and infinite from where you're lying right now, but from the perspective of the planet itself, it is a fragile, paper-thin shell, a breath of air clinging to a rock in space. Earth's atmosphere is divided into 5 distinct layers, each one stranger than the last. The layer you are breathing right now is called the troposphere. It extends from the ground up to roughly 12 kilometers at the equator and a little lower at the poles. This is where all weather happens. Clouds, rain, wind, storms, the movement of air that shapes climates and carries moisture across continents. The troposphere is turbulent and alive and constantly in motion. Above it sits the stratosphere, calmer and colder, where the ozone layer lives and where high-altitude aircraft cruise in smooth, cloudless air. Then comes the mesosphere, a cold and almost airless realm where meteors burn up as they fall toward Earth, leaving the brief streaks of light we call shooting stars. Above that is the thermosphere, where temperatures can exceed 1,500 degrees Celsius, even though there is so little air that it would feel bitterly cold to a human body. And at the outermost edge, barely separated from space itself, is the exosphere, where individual atoms drift free of the planet's gravity and quietly escape into the void. 5 layers. 5 entirely different worlds, stacked one on top of another, all invisible from the ground. The color of the sky is one of the most beautiful accidents in physics. If you looked at sunlight through a prism, you would see all the colors of the spectrum. Sunlight contains them all. But when that light enters Earth's atmosphere, something selective happens. The gas molecules in the air, primarily nitrogen and oxygen, scatter shorter wavelengths of light more powerfully than longer ones. Blue light, with its shorter wavelength, gets scattered in every direction across the sky, while red and orange light passes through more directly. This is why the sky appears blue during the day and why it turns red and gold at sunset, when sunlight must travel through a much longer stretch of atmosphere before it reaches your eyes. From the moon, astronauts describe the sky as perfectly black even with the sun shining brightly, because there is no atmosphere to scatter the light. The blue that surrounds you every clear day is not a property of space or of the sun. It is a property of the air itself, a physical conversation between light and gas that has been happening above every living thing that ever walked this planet. The atmosphere has weight, and it is pressing down on you right now. The entire column of air above every square centimeter of your body exerts a force of about 10 newtons. roughly equivalent to a kilogram of weight per square centimeter. Over the area of an average human body, this amounts to a total force of approximately 15,000 kilograms pressing down from all directions at sea level. You don't feel it as a crushing weight because the air and fluids inside your body push back with equal force. But the pressure is real and it is constant. It decreases with altitude, which is why mountain climbers and pilots need supplemental oxygen at high elevations and why the ears pop in an airplane. Every breath you take exists because of this pressure driving air into your lungs with each inhalation. The atmosphere doesn't just sit above us. It leans against us, surrounds us, holds us in a gentle, continuous embrace from every direction. The ozone layer is a gift from ancient life. High in the stratosphere, roughly between 15 and 35 kilometers above the surface, lies a thin region of gas with an unusual molecular structure. Ozone, a molecule made of 3 oxygen atoms instead of the usual 2, accumulates here in concentrations that would be toxic at ground level, but that serve, at altitude, as one of the most important shields in the history of life on Earth. Ozone absorbs the majority of the sun's ultraviolet radiation, particularly the UVB and UVC wavelengths that would otherwise reach the surface and damage DNA, causing sunburn, skin cancer, and potentially disrupting the biological machinery of nearly every living organism on the planet. Before the ozone layer formed, life was confined largely to the oceans, shielded by water. It was the gradual buildup of oxygen in the atmosphere, produced over hundreds of millions of years by early photosynthetic life, that created the conditions for ozone to form. Life made the ozone layer, and the ozone layer made life on land possible. It is one of the most profound feedback loops in the history of the biosphere. Lightning strikes Earth approximately 100 times every second. At any given moment, roughly 2,000 thunderstorms are active somewhere on the planet. Together, they generate an average of 100 lightning bolts per second, which means that in the time you have been listening to this, several thousand lightning strikes have occurred across the globe. Each individual bolt can reach temperatures of around 30,000 Kelvin, approximately 5 times hotter than the surface of the sun, and can carry a current of up to 30,000 amperes. The thunder you hear afterward is the sound of the air around the lightning channel being superheated so rapidly that it expands explosively. Lightning is not just a weather phenomenon. It plays a role in the chemistry of the atmosphere, producing nitrogen compounds that eventually reach the soil and contribute to plant growth. Over the course of Earth's history, lightning may have played a role in the chemistry that led to the first complex organic molecules, the building blocks from which life eventually emerged. Every storm that lights the sky above you is part of a process that has been reshaping both the atmosphere and the biosphere since before there were eyes to watch it. The wind is the atmosphere thinking. Perhaps that is too poetic a way to put it, but the global circulation of air across Earth's surface is in many ways a kind of vast planetary computation, the atmosphere constantly solving the problem of unequal heating. The sun heats the equator more intensely than the poles, creating a difference in air temperature and pressure that drives enormous circulation systems. Warm air at the equator rises, flows toward the poles at high altitude, cools, sinks, and flows back toward the equator at the surface. These Hadley cells, as they are called, are part of a system of interlocking atmospheric circulation patterns that drives the trade winds, the jet streams, the monsoons, and the prevailing westerlies of the mid-latitudes. The rotation of the Earth bends these flows through the Coriolis effect, deflecting them to the right in the northern hemisphere and to the left in the southern. Every breeze you have ever felt, from the gentlest rustling of leaves to the most violent hurricane, is the atmosphere engaged in this ancient, ceaseless redistribution of heat from the tropics toward the poles. The jet stream is a river of air moving at incredible speeds high above your head. At altitudes of roughly 10 to 15 kilometers, near the boundary between the troposphere and the stratosphere, narrow bands of very fast-moving air encircle the planet. These are the jet streams, and they are extraordinary. They can reach speeds of more than 500 kilometers per hour, making them among the fastest sustained air movements on Earth. They form at the boundaries between cold polar air and warmer mid-latitude air, where the temperature contrast drives a particularly intense pressure gradient. Pilots have been using jet streams to reduce flight times since the mid-20th century, flying with the stream when heading east and routing around it when heading west. The jet stream also has a profound influence on weather. When it meanders in large waves, it can drag cold polar air deep into mid-latitudes, producing the kind of winter cold snaps that seem to descend from nowhere. And because the jet stream's behavior is connected to the temperature difference between the Arctic and the equator, changes in that difference due to warming may be affecting how the jet stream behaves, with consequences for weather patterns across the entire northern hemisphere. Clouds are not made of water vapor. This is a remarkably common misconception. Water vapor is an invisible gas, and it is indeed present in the atmosphere and plays a crucial role in weather and climate. But clouds, the visible masses of white and gray that drift across the sky above you, are made of tiny liquid water droplets, or ice crystals, suspended in the air. Clouds form when moist air rises and cools to the point at which water vapor condenses around tiny particles called condensation nuclei, which can be dust, pollen, sea salt, or even pollution particles. The droplets are so small and light that they remain suspended by air currents even though water is denser than air. A typical cumulus cloud can contain hundreds of millions of kilograms of liquid water, yet it floats effortlessly in the sky because the water is distributed across billions of tiny droplets spread through an enormous volume of air. Clouds are one of the most important regulators of Earth's climate, reflecting incoming sunlight back to space and trapping outgoing heat, and scientists still have significant uncertainty about exactly how clouds will change as the planet warms, making them one of the largest sources of uncertainty in climate projections. The aurora borealis is a conversation between the sun and the atmosphere. High above the Arctic and Antarctic circles, on clear dark nights, curtains and ribbons of green, red, and violet light drift and shimmer across the sky in one of the most beautiful natural displays on Earth. The northern lights, or aurora borealis, and their southern counterpart, the aurora australis, are produced by a process that begins 93 million miles away at the surface of the sun. The sun constantly streams a flow of charged particles, mainly electrons and protons, into space. This is the solar wind. When it reaches Earth, most of it is deflected by the planet's magnetic field. But near the magnetic poles, where the field lines converge and dip toward the surface, some of these particles can travel down into the upper atmosphere and collide with oxygen and nitrogen molecules. These collisions excite the molecules, and when they return to their ground state, they release energy as light. Green auroras come primarily from oxygen at altitudes of around 100 kilometers. Red auroras come from oxygen at higher altitudes, above 200 kilometers. Blue and purple come from nitrogen. The entire display is the atmosphere glowing with the energy of the sun, channeled by the invisible architecture of Earth's magnetic field, playing out in silent color thousands of feet above the dark polar ground. The atmosphere contains a layer that reflects radio waves and makes long-distance communication possible. At altitudes of roughly 60 to 1,000 kilometers in the region called the thermosphere lies a region of the atmosphere where solar radiation ionizes gas molecules, stripping electrons from atoms and creating a layer of electrically charged plasma. This is the ionosphere and has played a remarkable role in human history. Radio waves transmitted from the surface can bounce off the ionosphere and return to the surface thousands of kilometers away, allowing radio signals to travel far beyond the horizon. This property made long-distance radio communication possible long before satellites existed and was essential for navigation, broadcasting, and military communication for much of the 20th century. The ionosphere fluctuates with solar activity, time of day, and season, which is why certain radio frequencies work better at night or during different seasons. During intense solar storms, it can be disrupted entirely, interfering with communications and GPS signals. This charged layer of the upper atmosphere is in constant dialogue with the sun, absorbing its radiation and responding to its moods in ways that ripple all the way down to our technology. There is a region above the clouds where lightning travels upward rather than down. Most lightning, as you know, strikes downward from clouds to the ground. But in the late 20th century, pilots and researchers began documenting strange luminous phenomena occurring above thunderstorms, shooting upward toward space rather than downward toward Earth. These are called transient luminous events, and they are extraordinary. Red sprites are large, diffuse flashes of red light that occur tens of kilometers above thunderstorms, lasting only a few milliseconds. Blue jets are focused, narrow streams of blue light that shoot upward from the tops of thunderclouds toward the stratosphere. Elves are brief rings of glowing light that expand rapidly at the base of the ionosphere, caused by the electromagnetic pulse from a lightning strike below. and gigantic jets. The most dramatic of all can extend all the way from the cloud tops to the ionosphere, briefly connecting the thunderstorm with the upper atmosphere in a single spectacular discharge. These phenomena were largely unknown to science before the 1990s, and they are still not fully understood. The atmosphere above thunderstorms turns out to be full of electrical activity that we never suspected, extending the story of lightning far above the clouds. The sky transitions from blue to black faster than most people realize. Astronauts aboard the International Space Station experience 16 sunrises and 16 sunsets every 24 hours as they orbit the Earth at approximately 400 kilometers of altitude, and each time the transition between day and night across the atmosphere is visible as a thin, vivid band of color along the edge of the planet. From that altitude, the atmosphere is clearly visible as a thin glowing shell, blue near the surface and fading rapidly to black. The point at which the sky transitions from breathable air to essentially vacuum is not a sharp line, but a gradient, a gradual thinning. Most of the atmosphere is below 30 kilometers. By 50 kilometers, 99.9% of the atmosphere's mass is below you. By 100 kilometers, the internationally recognized boundary called the Kármán line, the air is so thin that aerodynamic surfaces no longer generate meaningful lift, and you are, by convention, in space. 100 kilometers. A distance that a car could cover in less than an hour. The difference between everything and nothing, between sky and space, between home and the void. The atmosphere breathes with the seasons. If you were to measure the concentration of carbon dioxide in the atmosphere over the course of a year, you would see something remarkable. The level rises through the northern hemisphere's autumn and winter and falls through the spring and summer. This annual fluctuation is the atmosphere breathing in synchrony with life on Earth. During the growing season in the vast northern land masses, where most of the world's forests, grasslands, and agricultural areas are concentrated, plants absorb carbon dioxide through photosynthesis, drawing it down from the air. When those plants die back or lose their leaves in autumn, the decomposition of organic matter releases carbon dioxide back into the atmosphere. The net result is a seasonal pulse of approximately 5 to 8 parts per million in the global carbon dioxide record. Scientists have been able to detect this pattern in data from monitoring stations around the world, and it is sometimes described as the planet breathing, the biosphere exhaling in winter and inhaling in summer. Embedded within this seasonal rhythm is the longer-term trend of rising carbon dioxide driven by the combustion of fossil fuels, a line that rises year after year even as it fluctuates with the seasons. Meteorites mostly burn up in the mesosphere. Every day, roughly 100 tons of material from space enters Earth's atmosphere. Most of this is microscopic dust, tiny grains that drift down through the atmosphere without burning or being noticed. But larger objects, from the size of a grain of rice to the size of a house, enter the atmosphere at speeds typically ranging from 11 to 70 kilometers per second. At these speeds, the friction of even the thin upper atmosphere generates enormous heat. The object begins to ablate, its surface material vaporizing as it is stripped away layer by layer. The glowing trail of vaporized material is what we see as a meteor or shooting star. Most meteors burn up completely in the mesosphere between 50 and 80 kilometers of altitude, well above where any airplane flies, leaving nothing but a brief light and a faint trail of ionized gas. The Earth is constantly being pelted from above, and the atmosphere quietly absorbs almost all of it, converting billions of tiny cosmic projectiles each year into harmless streaks of light in the night sky. Sound cannot travel through space, but it travels very differently through different layers of the atmosphere. Sound requires a medium to travel through, which is why the vacuum of space is silent. But Earth's atmosphere provides that medium, and sound behaves in interesting ways as it moves through air of varying temperature, pressure, and density. At sea level, sound travels at roughly 340 meters per second, a speed that varies with temperature. In the stratosphere, where temperature increases with altitude due to ozone-absorbing solar radiation, sound can be refracted back toward the ground, creating what are called infrasound shadow zones and acoustic ducting. Very large explosions or the booming of the waves can sometimes be heard at extraordinary distances because their low-frequency sound waves travel through these atmospheric waveguides. Infrasound, below the range of human hearing, can propagate thousands of kilometers through the atmosphere and is used by monitoring networks to detect nuclear explosions and large volcanic eruptions. The atmosphere is not silent. It hums with low-frequency sounds below the threshold of human hearing, carrying the signatures of storms, surf, earthquakes, and distant explosions across the planet in a continuous subsonic conversation. Earth's magnetic field and the atmosphere work as a team to protect life. The planet's magnetic field, generated by the churning of molten iron in the outer core thousands of kilometers below your feet, extends far into space, creating a region called the magnetosphere that deflects the most energetic charged particles in the solar wind. But the atmosphere handles the rest. Ultraviolet radiation that gets past the magnetosphere is largely absorbed by the ozone layer. X-rays from the sun are absorbed in the upper atmosphere. Gamma rays and most cosmic rays are stopped before they reach the surface. Together, the magnetosphere and the atmosphere provide a layered, redundant system of protection that makes the surface of Earth habitable. Without the magnetic field, the solar wind would gradually strip the atmosphere away, as it has done on Mars, which lost its magnetic field billions of years ago and is now left with an atmosphere less than 1% as dense as Earth's. Without the ozone layer, ultraviolet radiation would sterilize most life on the surface. Life on Earth exists in a very carefully protected space, shielded from the violence of the cosmos by invisible fields and invisible chemistry above. Clouds are given Latin names based on a system invented by a 19-year-old amateur scientist in 1802. The system we use to classify clouds, which you encounter in weather forecasts and meteorology textbooks around the world, was devised by a young English pharmacist and amateur naturalist named Luke Howard. In 1802, Howard presented a paper to a small scientific society in London in which he proposed a classification system for clouds using Latin terms, cirrus meaning curl of hair, cumulus meaning heap, stratus meaning layer, and nimbus meaning rain. His system was elegant, practical, and descriptive, and it was adopted broadly and rapidly. The World Meteorological Organization's current cloud atlas, which recognizes 10 basic cloud genera and dozens of species and varieties, still rests on the foundations that Howard laid more than 200 years ago. The names you might notice on a weather radar: cumulonimbus for the towering thundercloud, cirrostratus for the thin high sheet that gives halos around the moon, altostratus for the gray mid-level layer, all descend directly from that single presentation by a teenage pharmacist who looked up at the sky and decided to give what he saw a proper name. The atmosphere was once radically different from what it is today. The atmosphere you are breathing tonight is not the atmosphere that Earth was born with. When the planet formed roughly 4.5 billion years ago, its earliest atmosphere was likely a mix of hydrogen, helium, methane, and ammonia, swept away relatively quickly by solar radiation and volcanic activity. The second atmosphere, released from volcanic eruptions over hundreds of millions of years, was rich in carbon dioxide, nitrogen, and water vapor, with essentially no free oxygen. Life existed in this early atmosphere, but only in anaerobic forms, organisms that do not use oxygen and would, in fact, be poisoned by it. The transformation came gradually, beginning around 2.7 billion years ago, when cyanobacteria began performing oxygenic photosynthesis, releasing free oxygen as a byproduct. This oxygen, which was initially toxic to most existing life, accumulated in the atmosphere over hundreds of millions of years in what geologists call the Great Oxidation Event. Most existing life was killed or forced into oxygen-free niches, but the survivors and the new life that evolved in the oxygen-rich atmosphere eventually led, through billions of years of evolution, to every breathing creature that has ever lived, including you, lying still right now, drawing in the oxygen that ancient microbes made. The greenhouse effect is ancient and essential, even before it became a problem. The term greenhouse effect carries significant negative connotations today, and with good reason. But the greenhouse effect itself is not a modern invention. It is an ancient, fundamental, and necessary property of Earth's atmosphere. Certain gases, primarily water vapor, carbon dioxide, methane, and nitrous oxide, are largely transparent to incoming visible sunlight but absorb outgoing infrared radiation, the heat that Earth's surface radiates back toward space. By trapping some of this outgoing energy, these greenhouse gases keep Earth's average surface temperature at around 15 degrees Celsius rather than the minus 18 degrees it would be without them. Without any greenhouse effect, The oceans would be frozen and life as we know it would not exist. The problem is not the greenhouse effect itself, but the enhancement of it. Since the Industrial Revolution, the concentration of carbon dioxide in the atmosphere has risen from approximately 280 parts per million to over 420 parts per million, an increase of roughly 50% in roughly 200 years. The atmosphere's chemistry has changed faster in that time than at almost any point in the geological record, and the consequences of that rapid change are playing out in the global climate system in real time. A single volcanic eruption can change the climate of the entire planet. In 1815, Mount Tambora in what is now Indonesia erupted in the most powerful volcanic explosion in recorded human history. The eruption ejected an estimated 150 cubic kilometers of material into the atmosphere, including enormous quantities of sulfur dioxide gas. In the stratosphere, this sulfur dioxide reacted with water to form sulfate aerosols, tiny reflective particles that spread around the globe over the following months. These aerosols reflected enough incoming sunlight to lower global temperatures by roughly 1 degree Celsius for the next 2 years. The following year, 1816, became known as the year without a summer. Crops failed across Europe and North America. Frosts occurred in June in New England. Famine and disease spread across the world. The eruption of a single volcano had altered the atmosphere enough to reshape the growing season for an entire year on the other side of the planet. Scientists study these historical events partly because they offer a kind of natural experiment in atmospheric intervention, and partly because they underscore how sensitive the climate system is to changes in the composition and reflectivity of the atmosphere. The sky above Antarctica sometimes shows clouds made of ice crystals at the edge of space. In the coldest regions of Earth's mesosphere, at altitudes of around 80 to 85 kilometers and temperatures that can drop below minus 130 Celsius, something remarkable and beautiful occasionally forms. Noctilucent clouds, also called polar mesospheric clouds, are the highest clouds in Earth's atmosphere, made of tiny water ice crystals that form in the extreme cold of the upper mesosphere. They are visible only during summer twilight in high-latitude regions, when the sun is just below the horizon, leaving the lower atmosphere in darkness while still illuminating these high, thin clouds in a ghostly blue-silver light. They are otherworldly in appearance, rippled and feathery, nothing like the clouds you see during the day. They were first documented in the late 19th century and have been observed at increasingly lower latitudes in recent decades, a pattern that researchers suspect may be connected to changes in the upper atmosphere. They are one of the atmosphere's most beautiful secrets, rarely seen, barely understood, and hovering at the very boundary between sky and space. The pressure of the atmosphere varies not just with altitude but with time, and it shapes your body in ways you might not expect. Barometric pressure, the weight of the air column above a given point, changes continuously with weather systems. High-pressure systems bring clear, calm conditions. Low-pressure systems bring cloud, wind, and rain. But these pressure changes also have biological effects that have been studied and documented, though not always fully explained. Some people report joint pain, headaches, and changes in mood associated with falling barometric pressure before storms. The mechanisms are not entirely clear, but may involve the expansion of gases in body cavities, changes in blood vessel diameter, or the sensitivity of fluid-filled joints to small changes in external pressure. The atmosphere's weight is not constant. It fluctuates day to day and hour to hour, and the living body, finely tuned to its normal environment, notices these fluctuations in ways that most people never consciously register, but that some feel acutely. The atmosphere contains billions of tons of living organisms. When people think about life on Earth, they think about the surface, forests and oceans and soils teeming with organisms of every kind. But the atmosphere is itself a living space. Bacteria, fungal spores, pollen, algae, and viruses are carried into the atmosphere by wind, rain, and turbulence, and can be transported thousands of kilometers before settling back to the surface. Scientists studying air samples at altitudes of several kilometers have found living microbes that appear capable of metabolic activity, surviving the UV radiation and desiccation of the upper atmosphere through mechanisms that are still being studied. These airborne microbes may play roles in cloud formation, as some bacteria can serve as ice-nucleating particles around which cloud droplets form. The atmosphere is not a sterile, abiotic layer above the biosphere. It is part of the biosphere itself, a thin aerial ecosystem where microscopic life drifts and circulates on a planetary scale, invisible to us but present in every breath of outdoor air. There is a pause in the atmosphere where the temperature stops falling and starts rising again. As you move upward through the troposphere, the air gets colder, roughly 6.5 degrees Celsius for every kilometer of altitude gained. This is why mountain peaks are cold and why high-altitude aircraft need heated cabins. But at roughly 12 kilometers, something changes. The temperature stops dropping. It levels off, and then as you continue upward through the stratosphere, it actually starts to increase again. This reversal of the normal temperature gradient is called the tropopause, the boundary between the troposphere and the stratosphere. It exists because the stratosphere is heated from above by the ozone layer's absorption of ultraviolet radiation, creating a temperature profile that is the inverse of the troposphere's. This temperature inversion is also what prevents weather from extending into the stratosphere. When rising air parcels hit the tropopause, they encounter air that is warmer and more buoyant than they are, and they stop rising. Thunderstorms can sometimes punch through the tropopause in their most intense updrafts, spreading anvil-shaped cloud tops at that boundary, but the stratosphere above remains perpetually calm and clear, a quiet ceiling above all the weather that moves through your daily life. The atmosphere influences ocean temperatures, and oceans influence the atmosphere in return. The relationship between the atmosphere and the oceans is one of the most important and complex partnerships in Earth's climate system. The atmosphere heats the ocean surface through radiation and warm air contact and cools it through evaporation. Winds drive ocean currents, pushing surface water across vast distances and generating the deep circulation patterns that redistribute heat around the planet. In return, the ocean's enormous thermal mass moderates the atmosphere, absorbing heat during warm periods and releasing it during cold ones, slowing the pace of climate change in ways that are measurable and significant. El Niño and La Niña events, periodic shifts in the temperature of the Central Pacific Ocean, reorganize rainfall patterns across much of the planet, causing droughts in some regions and floods in others, purely through changes in how the ocean and atmosphere exchange heat and moisture. These two enormous fluid systems, one of air and one of water, are constantly exchanging energy and water vapor in a dialogue that drives weather and shapes climate on timescales from weeks to millennia. Thunder has been heard over 200 kilometers away from a lightning strike. Under the right atmospheric conditions, in particular temperature inversions in the lower atmosphere that create channels for sound to travel, the very low-frequency components of thunder can propagate extraordinary distances. Thunder is typically audible to the human ear up to about 25 kilometers from a strike. But researchers using sensitive infrasound microphones have detected the low-frequency signatures of lightning at distances of hundreds of kilometers. In the 19th century, extraordinarily loud volcanic eruptions, including Krakatoa's catastrophic explosion in 1883, were heard at distances of over 4,000 kilometers across the Indian Ocean, Australia, and as far as Rodriguez Island near Mauritius. The sound traveled through the atmosphere multiple times, circling the globe on acoustic waveguides. The atmosphere is a resonating chamber of planetary scale, capable of carrying certain frequencies of sound with remarkable efficiency across distances that make the idea of sound as something local seem entirely inadequate. Every raindrop that falls has a story that begins in the ocean. The water cycle is one of the most elegant and ancient processes on Earth, and the atmosphere is its engine. Water evaporates from the ocean, mostly from the vast surface of the tropical oceans, and enters the atmosphere as water vapor, rising with warm air into the troposphere. As it rises and cools, it condenses around dust and salt particles to form cloud droplets. In certain conditions, these droplets collide and combine, growing until they are heavy enough to fall. Rain, snow, sleet, and hail are all forms of precipitation, water returning from the atmosphere to the surface after its journey through the sky. This journey takes different amounts of time depending on where the water goes. A water molecule that evaporates from the ocean today might fall as rain within a week or two. But water that falls as snow on a polar glacier can remain locked in ice for tens of thousands of years before returning to the ocean. On average, a water molecule spends about 9 days in the atmosphere between leaving the surface and returning to it. In those 9 days, it may have traveled thousands of kilometers, riding wind currents across oceans and continents, before falling gently somewhere it has never been before. The atmosphere creates the conditions for fire. and fire has shaped the atmosphere in return. Fire requires three things: fuel, heat, and oxygen. The third ingredient comes entirely from the atmosphere, specifically from the 21% of the atmosphere that is molecular oxygen, a proportion maintained by the balance between the photosynthesis of plants and the respiration and decay of all living things. For most of Earth's history, the oxygen concentration in the atmosphere was lower than it is today, and fire was correspondingly less frequent and less intense. During certain periods, such as the late Carboniferous period around 300 million years ago, oxygen concentrations may have risen to as high as 35%, which would have made fires far more intense and frequent than today. The charcoal layers preserved in ancient rock formations from that period confirm that fire was widespread. Today's 21% oxygen concentration seems to be near a balance point, high enough to support vigorous combustion, but low enough that the world's forests do not burn spontaneously. The atmosphere holds the conditions for fire in a kind of equilibrium, regulated by biology. The sound of the wind through trees is the atmosphere communicating its own motion to the world below. Everything you hear in the natural world that involves air movement is a message from the atmosphere. The rustling of leaves translates the invisible passage of air into something audible. The roaring of a storm converts the kinetic energy of moving air into sound waves that rattle windows and carry for kilometers. The whistle of wind around a building is the atmosphere finding resonant frequencies in man-made structures. Even the human voice is air set into vibration by the body, shaped by the mouth and throat, carrying through the atmosphere from one person to another. The atmosphere is the medium through which almost all sound on Earth travels, the invisible carrier that makes every spoken word, every piece of music, every bird song and thunderclap possible. You could think of every sound you have ever heard in your life as a message delivered by the air, which has been moving without rest since long before there were ears to hear it. High-altitude research balloons have been sent to the very edge of the stratosphere carrying instruments and cameras. The stratosphere is home to a steady stream of high-altitude research balloons launched by weather agencies, universities, and space programs around the world. These balloons, made of thin latex or polyethylene, are inflated with helium and rise steadily through the atmosphere, expanding as the surrounding air pressure drops, until they burst at altitudes of around 30 to 40 kilometers. On their way up, they carry instruments that measure temperature, pressure, humidity, ozone concentration, and other atmospheric properties, transmitting the data back to the surface before drifting down on a parachute. Some research balloons have also carried cameras that captured extraordinary photographs of the curvature of Earth and the inky blackness of space above the thin layer of blue atmosphere below. These images have a particular quality that photographs from orbit do not capture because they show the atmosphere from within as a visible layer, thin and fragile and luminous against the darkness of space. They are among the most quietly moving images of the planet ever taken. The troposphere contains almost all of the water in the atmosphere, yet it is extraordinarily dry. By any ordinary measure, the air feels wet. Humidity makes tropical days oppressive. Fog can reduce visibility to meters. Rain falls in torrents. And yet the total amount of water held in the atmosphere at any one time, almost entirely in the troposphere, is surprisingly small. If all the water in the atmosphere were to fall as rain simultaneously everywhere on Earth, it would form a layer only about 2.5 centimeters deep across the planet's entire surface. That is roughly equivalent to about 10 days' worth of global precipitation. The atmosphere is not a reservoir of water. It is a pathway, a rapidly moving transit system through which water passes from the ocean to the land and back again. The same water molecule that drenches a forest today was in the Indian Ocean a week ago, and next month it may be in the snowpack of a mountain, or in the vapor of an evening cloud, or in the water you drink from a glass in the dark of night. Some parts of the atmosphere are electrically connected to the ground below them in ways that affect all life. The atmosphere maintains a global electrical circuit, a continuous flow of electrical current that connects thunderstorms to the clear air above them and to the surface of the Earth below. At any given moment, roughly 2,000 thunderstorms around the planet are acting as generators, pumping positive charge upward into the ionosphere and negative charge down into the Earth's surface. In the clear air between thunderstorms, a gentle current flows downward from the ionosphere toward the surface. The result is that the atmosphere maintains a measurable electrical potential between the ionosphere and the ground, typically around 200,000 volts, with the ionosphere positive and the ground negative. This global circuit was first proposed by the physicist C.T.R. Wilson, who won the Nobel Prize for his work on cloud physics, and it has since been confirmed by measurements around the world. The Earth's surface itself is electrically active in ways that most people never consider, connected to every storm happening anywhere on the planet through the quiet electrical medium of the atmosphere. Dust from the Sahara Desert fertilizes the Amazon rainforest. In one of the most striking examples of how the atmosphere connects different parts of the Earth, researchers have traced the journey of dust particles lifted from the Baudelaire Depression, a dried ancient lake bed in the eastern Sahara, across the Atlantic Ocean to the Amazon basin in South America. Each year, an estimated 40 million tons of Saharan dust crosses the Atlantic in this way, carried by prevailing winds at altitudes of several kilometers. When it settles over the Amazon, this dust brings with it phosphorus and other minerals that are critically scarce in the tropical soils. The Amazon's extraordinary biological productivity depends to a significant degree on this annual supply of nutrients from a desert on another continent. The atmosphere is not just a carrier of weather. It is a planetary conveyor belt, moving the microscopic materials of life from one part of the world to another, connecting ecosystems across thousands of kilometers in ways that are invisible, unceasing, and essential. The rate at which the atmosphere spins is not the same at every latitude. Earth rotates as a solid body, which means that every point on the surface completes one full rotation in 24 hours. But the atmosphere, being fluid, does not rotate uniformly with the surface. At the equator, where the surface is moving fastest, the lower atmosphere generally follows the surface. But at higher altitudes and higher latitudes, the atmosphere can move quite differently from the ground below it. The jet streams, for example, move vastly faster than the surface beneath them. The overall pattern of atmospheric circulation involves air moving at different speeds and in different directions at different altitudes, creating the complex layering of winds that pilots navigate and meteorologists model. The atmosphere is not like a shell sitting fixed on a rotating planet. It is a dynamic, turbulent fluid with its own internal circulation, loosely coupled to the surface that drives it at the bottom and the sun that drives it from above. The highest clouds in the troposphere form at the boundary of the stratosphere and can be seen from hundreds of kilometers away. Cumulonimbus clouds, the towering thunderstorm clouds that can reach 15 kilometers or more in height, are among the most visually dramatic structures in the atmosphere. Their flat anvil-shaped tops, caused by the tropopause blocking further upward growth, can be seen from extraordinary distances. Pilots flying at cruise altitude will often see the tops of cumulonimbus cells from hundreds of kilometers away, catching the last light of the sun long after it is set below the horizon for those on the ground below. Inside a mature cumulonimbus, conditions are some of the most violent in the natural world. Updrafts can exceed 100 kilometers per hour, strong enough to suspend large hailstones for extended periods before they grow heavy enough to fall. Electrical charges build until they discharge as lightning. Winds at different levels within the storm can be moving in different directions, creating the turbulence that makes flying through a thunderstorm so dangerous. And yet from 100 kilometers away, seen against a sunset sky, one of these massive storm columns is simply beautiful, lit pink and gold, towering above everything around it, carrying its violence quietly in the distant air. The stratosphere is used by scientists to store records of Earth's chemical history. When substances enter the stratosphere, they can remain there for years or decades, much longer than materials cycle through the troposphere where rain scavenges particles and gases from the air within days. This long residence time makes the stratosphere a kind of atmospheric archive. Volcanic eruptions inject sulfur dioxide and ash into the stratosphere, and the signatures of major eruptions can be preserved in ice cores drilled from glaciers, where the annual layers of snowfall trap particles from the air at the time of deposition. These records allow scientists to reconstruct the history of volcanic activity over hundreds of thousands of years. Similarly, the stratospheric chemistry disrupted by the use of chlorofluorocarbons in the late 20th century, leading to the ozone hole over Antarctica, provided one of the clearest demonstrations of how human industrial activity could alter the chemistry of the atmosphere in ways detectable on a global scale. The stratosphere remembers what has passed through it, and careful reading of that memory tells the story of both the planet's natural history and the footprint of human civilization. Winds at the surface of Earth are named in the direction from which they blow, not toward which they travel, A north wind blows from the north toward the south. This is a convention that has been used by mariners, farmers, and meteorologists for centuries, and understanding it changes the way weather forecasts read. Trade winds in the tropics blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, driven by the large-scale Hadley cell circulation and deflected by the Coriolis effect. These winds were named by early sailors because they were reliable enough to be traded upon, the dependable air currents that made the great oceanic voyages of exploration possible. The prevailing westerlies of the mid-latitudes blow from the west, bringing the characteristic weather patterns of temperate climates. Polar easterlies blow from the east at high latitudes. These broad patterns of surface wind have been shaping human migration, agriculture, trade routes, and warfare for as long as people have sailed ships and planted crops. The atmosphere's circulation is not just a physical system. It has been a fundamental driver of human history. The atmosphere can form ice in ways that seem to violate ordinary physics. Normally, water freezes at 0 degrees Celsius at sea level. But in the atmosphere, under the right conditions, water droplets can remain liquid at temperatures well below freezing, sometimes as cold as -40 Celsius. These are called supercooled water droplets, and they exist in liquid form because they lack the nuclei around which ice crystals typically form. When an aircraft flies through a cloud of supercooled droplets, the impact provides that missing nucleation point, and the water can freeze almost instantly on the aircraft's surface, a phenomenon called airframe icing that has been responsible for numerous aviation accidents and is carefully monitored in weather forecasts for pilots. Supercooled droplets can also freeze instantly on trees, power lines, and ground surfaces during freezing rain events, coating everything in a layer of clear ice that is both beautiful and destructive. The atmosphere regularly operates outside the simple rules of temperature and phase change that describe water at the surface, producing ice in places and in ways that depend on conditions far more subtle than a thermometer reading. Some animals use atmospheric pressure changes to predict the weather. For centuries, farmers, sailors, and naturalists have observed that certain animals seem to behave differently before storms arrive, before the sky changes, and before any wind picks up. Horses become restless. Cows lie down. Insects disappear indoors. Birds fly lower. Sharks have been tracked moving to deeper water before hurricanes. Many of these observations have anecdotal origins, but some have been investigated scientifically. Several species of fish appear sensitive to the pressure changes associated with approaching weather systems, adjusting their depth in the water to compensate. Some insects carry pressure-sensitive organs that respond to barometric changes. The mechanism by which animals might sense atmospheric pressure changes likely involves organs that detect the compression of air pockets in the body, analogous to the way human sinuses can ache before a storm. The atmosphere communicates its coming changes to the biological world in subtle physical signals, and evolution has in some cases equipped living things with sensors to detect them, giving them a kind of weather sense that no technology is needed to explain. The amount of water vapor in the atmosphere varies enormously with latitude and temperature. Air's capacity to hold water vapor increases dramatically with temperature. Cold polar air can hold very little water vapor. Warm tropical air can hold vastly more. This is why tropical climates feel so humid and polar regions feel so dry. It is also why the tropics are the engine of global precipitation, where the combination of warm ocean temperatures and intense solar heating drives massive evaporation and the formation of the towering convective clouds that produce the world's most intense rainfall. The Intertropical Convergence Zone, a belt of low pressure near the equator where the trade winds of the two hemispheres meet and converge, is one of the wettest regions on Earth precisely because it sits above the warmest oceans and receives the most intense solar heating. As climate warms and the atmosphere holds more water vapor, researchers expect the global water cycle to intensify, with wet regions generally getting wetter and dry regions potentially getting drier, not because rainfall patterns shift dramatically, but because when it does rain, there is more water available in the air to fall. Space weather affects the atmosphere in ways that are only beginning to be understood. The sun is not a steady, unchanging source of light and heat. It is a dynamic and sometimes violent star subject to cycles of activity that include solar flares, coronal mass ejections, and variations in the solar wind. During periods of intense solar activity, enormous clouds of charged particles can be hurled toward Earth at millions of kilometers per hour. When these coronal mass ejections reach Earth, they compress the magnetosphere, drive electrical currents through the ionosphere, and can produce spectacular auroral displays at unusually low latitudes. But they can also disrupt satellite operations, interfere with radio communications, and induce currents in long electrical conductors like power transmission lines and pipelines, occasionally causing significant damage. In 1989, a powerful geomagnetic storm caused the complete collapse of the Hydro-Quebec power grid, leaving 6 million people without electricity for 9 hours. In 1859, the Carrington event, the most powerful geomagnetic storm in recorded history, induced currents so strong in telegraph wires that some operators received electric shocks and telegraph systems continued to function briefly even after being disconnected from their power sources. The outer atmosphere is the interface between Earth and the Sun's variable energy, and understanding that interface has become increasingly important as human technology becomes more dependent on satellites and electrical infrastructure. The entire atmosphere weighs about 5,000 million tons. If that number is hard to picture, consider it this way. The atmosphere is roughly equivalent in mass to a layer of water about 10 meters deep spread across the entire surface of the Earth. It is an enormous amount of material. And yet it is distributed through a volume so vast and composed mostly of gas so diffuse that we can walk through it without resistance, breathe it without noticing its weight, and look through it across the entire width of the solar system. The same material that would be an enormous crushing mass if compressed is, when spread through the volumes that the atmosphere occupies, so thin as to be nearly invisible. One of the great paradoxes of the air is that it is simultaneously one of the largest things surrounding us and the most transparent. The atmosphere supports an entire ecosystem of organisms that spend their entire lives aloft. Beyond the bacteria and spores that are transported through the atmosphere, there are organisms that genuinely live there, at least for extended periods. Certain species of swift spend almost their entire adult lives in the air, landing only to nest. The common swift can remain airborne for 10 months of the year, eating, drinking, sleeping, and even mating on the wing. Certain spiders release silk threads that catch the wind and carry them hundreds of kilometers in a process called ballooning. Monarch butterflies migrate thousands of kilometers through the atmosphere, navigating by a combination of the sun's position and a time-compensated internal clock. Albatrosses spend years at sea without landing, gliding on ocean winds with barely a wing beat. The atmosphere is not just the medium through which flying creatures pass. For some of them, it is home, a three-dimensional living space in which they feed, sleep, travel, and navigate with precision that our own aircraft can barely match. The chemistry of the atmosphere changes with altitude in ways that make each layer chemically distinct. The troposphere is where most atmospheric chemistry happens, driven by sunlight, water vapor, and the gases released by biological activity and human industry. Ozone in the troposphere, near the surface, is a pollutant formed by the reaction of nitrogen oxides and volatile organic compounds in sunlight, and it is harmful to lungs and vegetation. But the same molecule in the stratosphere is a protector, formed there by the reaction of oxygen with ultraviolet light and serving as a shield. The mesosphere contains metallic layers, thin strata of free metal atoms deposited by the constant slow rain of micrometeorites burning up above. Sodium, iron, magnesium, and other metals float in these ghostly layers, detectable by the way they scatter laser light beamed up from telescopes. The thermosphere, despite its name, would feel cold to a human body because its molecules are so few and far apart that they cannot transfer heat effectively, even though each individual molecule is moving extremely fast. The chemistry of the atmosphere is not uniform. It is a stack of distinct chemical environments, each operating by different rules, each shaped by the balance between solar radiation, gravity, and the biology of the planet below. The atmosphere has a memory. Changes to its composition persist for different lengths of time depending on the substance involved. Water vapor stays in the atmosphere for about 9 days on average before it falls as precipitation. Methane remains for roughly a decade before it is broken down by atmospheric chemistry. Carbon dioxide, by contrast, is extremely long-lived. Once emitted, carbon dioxide is distributed through the atmosphere, absorbed by the ocean and the biosphere, and cycles between these reservoirs over decades, centuries, and millennia. some fraction of carbon dioxide emitted today will remain in the atmosphere for thousands of years. Chlorofluorocarbons, the industrial gases that damage the ozone layer, persist for 50 to over 100 years. This difference in atmospheric lifetime is one of the reasons that the consequences of human emissions are not immediately reversed when emissions stop. The atmosphere holds the memory of what has been added to it and will continue to experience the effects long after the source has ceased. The atmosphere is not a blank slate that resets quickly. It is a system with a history, carrying the fingerprints of every large volcanic eruption, every wildfire season, every century of industrial activity in its slowly changing chemistry. Lightning can strike the same place many times, and the Empire State Building is hit roughly 23 times per year. The old saying that lightning never strikes the same place twice is not just wrong. It is almost exactly backwards for tall structures. Lightning tends to preferentially strike elevated points because they reduce the distance the electrical discharge needs to travel. The Empire State Building in New York City was struck so frequently that, for a period, it was used as a research station for lightning science, with instruments installed specifically to measure the characteristics of lightning strikes to the building. The building acts as a giant lightning rod, intercepting discharges that would otherwise strike the ground nearby. Tall trees are struck repeatedly for the same reason, and over time a frequently struck tree develops characteristic scarring and sometimes dies from the repeated damage. Lightning rods were invented by Benjamin Franklin in the 18th century, and the principle is simple. By providing a conducting path from the high point of a structure to the ground, you give the electrical discharge a preferred route that minimizes damage. The fact that lightning prefers the same spots again and again is not a quirk. It is a consequence of the same physics that governs all electrical discharge. The atmosphere makes the sun look larger at the horizon than it does overhead. When the sun or moon is near the horizon, it appears significantly larger than when it is high in the sky. This is entirely an optical illusion, not a real change in size or distance. The moon illusion, as it is known when applied to the moon, has been studied for centuries and is still not completely explained, though it appears to involve the way the brain interprets the size of objects near the horizon relative to the landscape below them. There is, however, a related real atmospheric effect. Near the horizon, sunlight travels through a much greater thickness of atmosphere than when the sun is overhead. This thicker atmospheric path causes the image to be blurred and spread, and the differential refraction of different wavelengths can stretch the solar disk slightly in the vertical direction. The famous green flash, occasionally visible at the very moment the sun dips below a clear ocean horizon, is a genuine atmospheric refraction effect, caused by the different degrees to which the atmosphere refracts different wavelengths of light. The green wavelengths linger briefly above the horizon after the red and orange have set, producing a flash of green that lasts only a second or two, seen by those watching closely at exactly the right moment. The atmosphere produces multiple rings, halos, and arcs of light that most people have never noticed. When the atmosphere contains high, thin cirrus clouds made of ice crystals, sunlight passing through those crystals at precise angles produces optical phenomena that can cover large arcs of the sky. A 22-degree halo, a ring of white light encircling the sun or moon at a fixed angular distance, is actually quite common, visible on roughly 1 in 3 days in many parts of the world, but most people simply never look up long enough to see it. Sundogs, also called parhelia, are bright spots of light that appear at the same altitude as the sun and approximately 22 degrees to either side, often with colored fringes. Circumzenithal arcs are bright, curved bands of prismatic color that arc above the sun when it is at low angles, and are sometimes described by those who see them as upside-down rainbows. Pillars of light appear to rise above or below the sun or artificial lights during cold weather when flat ice crystals are floating horizontally in the air. The atmosphere is constantly producing light phenomena of extraordinary beauty, and almost all of them go unnoticed because we have learned to stop looking up. Rainbows require both sunlight and rain in exactly the right geometry to form. A rainbow is not a physical object at a fixed location. It is an optical phenomenon that exists only in relation to your specific position. The sunlight must be behind you and the rain must be in front of you. Sunlight enters each raindrop, is refracted at the surface, reflected from the back, and refracted again on exit, with different wavelengths of light exiting at slightly different angles, spreading the white sunlight into its component colors. The primary rainbow's arc appears at approximately 42 degrees from the anti-solar point, the point in the sky directly opposite the sun from your position. This means that two people standing side by side do not see exactly the same rainbow. Each person sees light reflected from different raindrops at the angle appropriate for their position. A rainbow seen from an airplane can form a complete circle because there is no horizon to cut it off. The secondary rainbow that sometimes appears outside the primary is formed by light that has been internally reflected twice within each raindrop, which reverses the order of colors and reduces the brightness. The entire phenomenon is a consequence of the interaction between the atmosphere's water and the sun's light, performing the same geometry every time rain falls with sun behind you, as it has been doing above the planet since the first rainstorm fell on the first oceans. Some regions of Earth's atmosphere contain layers of warm air sandwiched between colder air below and above, creating temperature inversions that trap pollution and produce unusual optical effects. In a temperature inversion, the normal decrease of temperature with altitude is reversed. A layer of warm air sits above cooler air near the surface, acting like a lid that prevents the upward mixing that normally disperses surface pollutants. Cities and valleys or near mountains are particularly susceptible to these inversions, which can lead to the accumulation of smog and particulate matter at dangerous concentrations. Los Angeles, Beijing, Mexico City, and many other cities regularly experience severe pollution events caused by temperature inversions, but inversions also produce spectacular optical effects. Under certain inversion conditions, objects that are normally below the horizon can become visible through atmospheric refraction, lifted into apparent view by the bending of light through the temperature gradient. Ships can appear to float above the horizon. Distant coastlines that would normally be invisible can appear as ghostly images in the sky above the sea. These are called mirages, and they are not hallucinations or tricks of an exhausted mind. They are real optical phenomena, the atmosphere bending light in ways that reveal geography that distance would otherwise hide. The polar vortex is a large area of low pressure and cold air surrounding Earth's poles that affects weather far to the south. High above the polar regions, particularly during winter, a powerful circulation of cold air and strong winds forms in the stratosphere and troposphere. This is the polar vortex, and when it is stable and well organized, it keeps the coldest Arctic air locked over the polar regions. But when the polar vortex weakens or breaks down, fragments of the cold polar air can escape southward, bringing bitterly cold temperatures to mid-latitude regions that might otherwise be experiencing relatively mild winter conditions. These polar vortex disruption events can bring extreme cold to the eastern United States, Europe, or Asia, sometimes producing the coldest temperatures of the year and occasionally setting all-time low temperature records. The polar vortex itself is a permanent feature of the winter atmosphere, but its stability varies from year to year, and understanding what controls that stability has become increasingly important as researchers try to understand how climate change might affect the frequency of cold outbreaks far from the poles. The total amount of nitrogen in Earth's atmosphere is so enormous that if it were spread across the entire surface of the planet as a liquid, it would form a layer several meters deep. Nitrogen makes up approximately 78% of Earth's atmosphere, making it the most abundant gas by far. In absolute terms, the total mass of nitrogen in the atmosphere is approximately 4,000 trillion tons. This nitrogen is biologically essential. All proteins and DNA contain nitrogen atoms, and living organisms require nitrogen in reactive forms they can incorporate into their chemistry. But atmospheric nitrogen is molecular nitrogen, two atoms bonded so tightly together that most organisms cannot use it directly. The nitrogen cycle, in which specialized bacteria convert atmospheric nitrogen into reactive forms like ammonia, and other bacteria eventually return it to the atmosphere, is the critical link between the inert reservoir of atmospheric nitrogen and the living world. Without nitrogen-fixing bacteria in soils and oceans, the supply of usable nitrogen would gradually be depleted and life as we know it would become impossible. The vast nitrogen blanket of the atmosphere is not directly accessible to most life. It requires a biological conversion step, a reminder that the atmosphere and the biosphere are always in partnership, each depending on the other in ways that run deeper than they first appear. The atmosphere above Earth's poles is physically different from the atmosphere above the equator. Because Earth is a sphere and the sun's light strikes the equator at a higher angle than the poles, the troposphere is deeper at the equator than at the poles. The tropopause, the boundary between the troposphere and stratosphere, sits at roughly 16 to 18 kilometers above the equator and only about 8 to 10 kilometers above the poles. This means that the column of weather-bearing troposphere is roughly twice as deep in tropical regions as in polar ones. The stratosphere begins lower over the poles, and the cold polar stratosphere plays a specific role in ozone chemistry. The ozone hole that forms annually over Antarctica during the southern spring is connected to the extremely cold temperatures of the polar stratosphere, where special polar stratospheric clouds form at temperatures below -78 Celsius. The surfaces of these clouds catalyze reactions that convert relatively harmless chlorine reservoir molecules into active chlorine that rapidly destroys ozone when sunlight returns in spring. The geometry of the planet, the angle of sunlight, the depth of the atmosphere, and the chemistry of the air all interact to produce a seasonal phenomenon at the poles that has no equivalent at lower latitudes. Contrails from aircraft can spread and persist for hours, becoming indistinguishable from natural cloud cover. When a jet aircraft flies through cold, moist air at high altitude, the hot water vapor in its exhaust can condense and freeze around tiny particles from the engine exhaust, forming the white lines of cloud we call contrails, short for condensation trails. In dry air, contrails disappear quickly as the ice evaporates. But in air that is already near saturation with water vapor, contrails can persist and spread for hours, eventually expanding into broad sheets of cirrus cloud that are effectively indistinguishable from naturally occurring clouds. On days with heavy air traffic, spreading contrails can cover significant fractions of the sky over busy air corridors. After the September 11th attacks in 2001, when all commercial aviation over the United States was grounded for 3 days, researchers observed a slight increase in the daily temperature range across the country, suggesting that the normal contrail cover was measurably affecting the balance between incoming and outgoing radiation. It was a rare natural experiment that demonstrated the scale at which modern aviation was affecting the atmosphere above the world's busiest flight corridors. The speed of sound in the atmosphere depends on temperature, which is why thunder sounds different in summer and winter. Sound travels faster in warmer air because the molecules are moving more quickly and can transfer the compression wave more efficiently. At 20 degrees Celsius, sound travels at approximately 343 meters per second. At -20, it travels at around 319 meters per second. This temperature dependence has practical consequences. In very cold conditions, sound from distant sources can be heard with unusual clarity, because the temperature gradient near the ground can cause sound to curve back down toward the surface rather than spreading upward and dissipating. This is why voices carry farther on cold, still winter nights, why sounds seem to come from unexpected directions in foggy conditions, and why the boom of a distant thunderstorm sounds different on a hot summer day than it might in cooler weather. The atmosphere is not just a medium that carries sound uniformly. It is a dynamic medium whose properties vary continuously with temperature and humidity, bending, focusing, and absorbing sound in ways that shape the acoustic character of every outdoor environment. Some of the earliest evidence for the existence of the upper atmosphere came from observing meteors. Before the era of balloons, aircraft, and satellites, the only way to probe the upper atmosphere was through indirect observation. One of the key early clues about what lay above the visible sky came from careful observations of meteors, which were known to begin glowing at certain altitudes and to disappear at others. By observing the same meteor from two widely separated locations and triangulating its path, 19th and early 20th century scientists were able to estimate the altitudes at which meteors became visible and where they burned out. These observations placed the upper boundary of significant atmospheric density at roughly 80 to 100 kilometers in rough agreement with modern measurements. In this way, the brief streaks of burning rock falling from space gave humanity its first approximate map of how deep the atmosphere extended before any instrument had been sent to measure it directly. The same rocks that most people admire briefly as shooting stars were, for early scientists, instruments of atmospheric measurement. The atmosphere creates a greenhouse effect for radio waves as well as for heat. Just as certain atmospheric gases are transparent to visible light but absorb infrared radiation, creating the thermal greenhouse effect, the ionosphere is transparent to certain radio frequencies and opaque to others. Very low-frequency radio waves can penetrate the ionosphere and escape to space, which is one reason that long-wave radio transmissions can sometimes be received by satellites. but certain higher frequencies are reflected back to Earth, creating the bouncing effect that allows long-distance radio communication. The ionosphere essentially acts as a mirror for particular radio wavelengths, letting some through and reflecting others back. This selective interaction between the atmosphere and electromagnetic radiation extends across the entire spectrum. Visible light passes through easily, which is why we can see the stars. Most infrared is absorbed or blocked. X-rays and gamma rays are almost entirely absorbed. Radio waves interact in complex ways depending on their frequency. The atmosphere is transparent to the light we see, but is in constant conversation with the full spectrum of electromagnetic radiation that the sun and the cosmos send toward us. The atmosphere is slowly leaking into space, and this process has been happening for billions of years. Earth's gravity holds the atmosphere tightly, but not perfectly. In the uppermost atmosphere, the exosphere, gas molecules that are moving fast enough can escape gravity entirely and drift off into space. This process, called atmospheric escape or outgassing, is happening right now, though very slowly. Light gases like hydrogen and helium escape most readily because their molecules move faster at a given temperature than heavier molecules like oxygen and nitrogen. This is why Earth's atmosphere contains very little hydrogen, even though hydrogen is the most abundant element in the universe. Over the history of the solar system, Earth has lost enormous amounts of hydrogen to space in this way. Mars and Venus also lose atmospheric gas to space, a process that has been measured by orbiting spacecraft. For Mars, which has a weaker gravitational field and no magnetic field to protect it from the solar wind, atmospheric escape has been so severe over billions of years that the planet has been stripped of most of the thick atmosphere it may once have had. Earth's continuing atmospheric escape is negligible on human timescales, but over geological time, it has shaped the composition of the air we breathe. The formation of dew on grass each morning is a quiet demonstration of one of the atmosphere's most fundamental properties. When the ground cools overnight by radiating heat away into the cold sky, the air immediately above the surface can cool below its dew point, the temperature at which the air can no longer hold all its water vapor as gas. At that point, water vapor condenses onto the cool surface of grass, leaves, spider webs, and any other solid surface, forming the tiny droplets we call dew. Each droplet is a tiny piece of cloud, essentially a condensation of water vapor onto a surface instead of onto a floating particle. On clear nights with light winds, cooling by radiation is most efficient and dew formation is heaviest. On cloudy nights, the clouds act as a blanket, reducing the radiation of heat from the surface, and dew may not form at all. In some very dry climates with cool nights, the dew collected by plants, rocks, and specially designed fog collection structures can be an important source of water. The morning dew is not exotic or surprising from a scientific point of view. It is the atmosphere simply doing what it always does when it meets a surface cool enough to cause condensation. But there is something quietly lovely about it nonetheless, the world rehydrating itself in the dark from the water vapor that was invisible in the air all day. The atmosphere makes the horizon possible. Without an atmosphere, looking outward from Earth's surface would be simply looking into space with stars visible in every direction, including across the surface. But because the atmosphere scatters sunlight during the day, the sky appears bright and blue in every direction above the horizon, and the ground appears lit by that scattered light rather than by direct sunlight alone. The horizon itself is the boundary between the lit atmosphere above and the ground below. In space, there is no equivalent. Astronauts on the surface of the moon see a sky that is always black, even when the sun is high above them, because there is no atmosphere to scatter the light. The stars are visible in the daytime on the moon alongside the blazing sun, something that is impossible on Earth under the blanket of scattered blue light. The familiar appearance of Earth's sky, the progression from the deep blue overhead to the pale blue or white near the horizon, the warm colors of sunset, the brightness of the daytime sky that makes the stars invisible, all of these are consequences of the atmosphere's interaction with light. Without the atmosphere, the sky would not be a sky. It would be space. There are rivers of water vapor in the atmosphere that carry more water than the Amazon. In the mid-latitudes, the atmosphere occasionally concentrates enormous amounts of water vapor into narrow, fast-moving streams called atmospheric rivers. These features, which can be thousands of kilometers long but only a few hundred kilometers wide, can transport water vapor at rates comparable to or exceeding the flow of the largest rivers on Earth. When an atmospheric river makes landfall on a coastal mountain range, it can deliver extraordinary amounts of precipitation in a short time. The western coast of North America, particularly California and the Pacific Northwest, receives much of its annual precipitation in a small number of atmospheric river events, and these events can be responsible for both beneficial reservoir replenishment and catastrophic flooding. The term atmospheric river was coined only in the 1990s, though the phenomenon itself has been occurring for as long as there have been oceans and atmosphere. It is another example of how the atmosphere operates at scales that dwarf human geography, moving water in quantities that make our rivers and reservoirs seem very small. The atmosphere has been altered by life more profoundly than life has been altered by the atmosphere. The story of Earth's atmosphere and the story of life on Earth are inseparable, but the direction of influence has been primarily from life to atmosphere rather than the reverse. Before life, the atmosphere had no free oxygen. Life created the oxygen. Before multicellular organisms, there was no ozone layer. The ozone layer created by oxygen-producing life made the land habitable. The composition of the nitrogen in the atmosphere is maintained partly by biological processes. The carbon cycle, which regulates the amount of carbon dioxide in the atmosphere and therefore the temperature of the planet, is driven largely by the balance between photosynthesis and respiration. The methane in the atmosphere comes mainly from biological sources, including wetlands, ruminant animals, and the decomposition of organic matter. The sulfur compounds in the atmosphere over the ocean are released by marine algae. In almost every major atmospheric constituent, and in many minor ones, biology has its fingerprint. The atmosphere is not just a physical and chemical system that passively surrounds the biosphere. It is partly a product of the biosphere, shaped over billions of years by the metabolism, death, and evolution of living things. You are not just breathing an atmosphere that supports life. You are breathing an atmosphere that life made. The atmosphere above large cities is measurably different from the atmosphere above open countryside. Human activity has changed the chemistry and particle content of the lower troposphere in ways that are now significant on a global scale. Cities produce enormous quantities of nitrogen oxides from vehicles and industry, volatile organic compounds from paints, solvents, and fuels, and particulate matter from combustion, construction, and road dust. These substances react in sunlight to form tropospheric ozone and secondary organic aerosols, creating the photochemical smog that reduces visibility and affects health in urban areas. But the influence extends beyond city boundaries. Pollution from major cities can be detected hundreds of kilometers downwind. The air over the remote Pacific Ocean carries trace signatures of Asian industrial emissions. The Atlantic Ocean atmosphere contains particulate matter from European and North American sources. The lower atmosphere is not divided into clean regions and dirty regions by any natural boundary. It is a connected system in which every emission eventually disperses into the global reservoir of air. The chemistry of the atmosphere you are breathing right now contains atoms and molecules that have passed through factories, vehicles, forests, oceans, volcanic eruptions, and the lungs of billions of other living things across the entire planet. The atmosphere has been explored by instruments on balloons, aircraft, rockets, and satellites, but most of it has never been directly sampled. Despite decades of atmospheric research, direct measurements of the atmosphere are sparse compared to its enormous volume. Weather balloons reach about 30 kilometers. Research aircraft typically operate below 20 kilometers. Sounding rockets can probe the mesosphere, but only briefly and in small numbers. Satellites orbit above the atmosphere and measure it from outside using various remote sensing techniques. The result is that our knowledge of atmospheric chemistry, dynamics, and composition at many altitudes is based primarily on indirect measurements and computer models. The models have become extraordinarily sophisticated, but they are still simplifications of a system of almost incomprehensible complexity. The atmosphere has around 500 million trillion molecules per cubic centimeter at sea level. Even the most powerful computers cannot track individual molecules. Everything we know about the atmosphere is a statistical description, an average over enormous numbers of particles. And the finer details of how those particles interact in specific conditions continue to produce surprises. Some atmospheric phenomena are so large that they can only be properly appreciated from space. The largest single weather systems on Earth, The major ocean storm systems and the long-lived blocking anticyclones that can persist for weeks and reshape weather across entire continents are visible as coherent structures in satellite imagery, but impossible to perceive as unified objects from any point on the ground below them. Hurricane systems can span hundreds of kilometers. The polar vortex, as discussed, encompasses an entire polar region. The intertropical convergence zone stretches around the entire circumference of the planet. These planetary-scale features were largely theoretical constructs before the space age, inferred from scattered surface observations but never directly seen. The first weather satellites in the early 1960s transformed atmospheric science by revealing for the first time that the atmosphere had a structure at scales visible only from above. Images of cloud patterns from space showed spiraling storm systems and vast bands of cloud in ways that were immediately legible as weather to the trained eye, and that conveyed the true global scale of atmospheric circulation in a way that no map of surface measurements ever had. The atmosphere is never completely still. At every point in the atmosphere, at every altitude, and in every location, the air is in motion. Even inside a sealed room, air molecules are moving at hundreds of meters per second, bouncing off each other and off the walls in the random thermal motion that gives the air its pressure and temperature. At larger scales, there is no such thing as perfectly calm air. What we call a calm day is air moving at less than about 1 meter per second near the surface, which feels like stillness to a person standing in it. But at higher altitudes, the atmosphere is always moving, driven by temperature differences, pressure gradients, the rotation of the Earth, and the influence of the solar wind on the upper layers. The atmosphere is a fluid in perpetual motion, constrained by gravity above and below, driven by the uneven heating of a spherical planet by a distant star, and shaped by the chemistry and biology of the surface below it. Even on the quietest night you have ever experienced, with no leaf moving and no sound in the air, the atmosphere above you was in motion all the way to the edge of space, turning and flowing and responding to forces that never stop. Water ice crystals in the upper atmosphere can create optical phenomena visible for hundreds of kilometers. The thin, high cirrus clouds made of ice crystals that drift at altitudes of 6 to 12 kilometers are not just passive features of the atmosphere. They are optical instruments, refracting and reflecting sunlight in ways that produce some of the most beautiful and varied displays of light visible from the ground. The 22-degree halo around the sun or moon, sun dogs, circumzenithal arcs, tangent arcs, and pillar of light displays are all produced by the interaction of sunlight with these ice crystals as they drift in characteristic orientations through the still cold air of the upper troposphere. Each phenomenon requires crystals of a specific shape and orientation, and the variety of optical effects visible from the ground reflects the variety of ice crystal types in the atmosphere above. On days when high cirrus is widespread, several different optical phenomena can be visible simultaneously, creating complex patterns of light and color across the sky that most observers never notice because they have never been told to look for them. The atmosphere above you on a clear day with high cloud is frequently performing these quiet light shows, and they require no special equipment to see, only the knowledge that they exist and the willingness to look up. The way clouds move across the moon on a clear night is one of the atmosphere's most quietly hypnotic displays. High thin clouds catching moonlight and drifting slowly across the bright disk produce a softening and diffusing of the moonlight that has been observed and written about for as long as people have watched the sky. Thicker cloud layers moving faster can alternately reveal and obscure the moon, creating the shifting patterns of light and shadow on a moonlit night that feel ancient and calm. The clouds themselves are made of the same water that fell as rain and flowed in rivers and evaporated from oceans and rose in warm air before cooling into tiny droplets at altitude. They are temporary structures, constantly forming and dissolving, their shapes determined by the temperature, humidity, and wind shear of the moment. A cloud that looks solid from below is, from within, simply a region of slightly reduced visibility, the droplets so small and dispersed that they barely obstruct the path of a hand reaching through them. Each cloud is a moment in the water cycle, caught briefly in visible form before it disperses or falls as rain. The ones moving across the face of the moon tonight, or on any clear night with high thin cloud, are just the atmosphere doing what it always does, carrying water from one place to another in the form of ice crystals, briefly made beautiful by the light of a distant world. The northern and southern lights have been seen as far from the poles as the tropics during the most powerful solar storms. Under ordinary conditions, auroras are confined to the high latitude regions near the magnetic poles, the auroral zones that ring the Arctic and Antarctic at roughly 60 to 70 degrees of latitude. But during particularly intense geomagnetic storms, when a large coronal mass ejection from the sun compresses and distorts Earth's magnetosphere severely, the auroral oval expands dramatically toward the equator. During the Carrington event of 1859, auroras were reported as far south as the Caribbean and Hawaii, at latitudes where the phenomenon had never been seen before. In more recent major storms, auroras have been visible in the mid-latitudes of Europe and North America. Each time this happens, people who have never seen the lights before suddenly look up at a sky full of green and red curtains and describe the experience as one of the most astonishing things they have ever witnessed. The lights are not rare in the sense of being unusual. Somewhere near the poles, they appear on most clear nights. They are rare only in the sense of requiring travel or fortune to see, but the atmosphere produces them continuously, as it has been doing since long before the first human eye looked up to wonder what was moving in the dark. The smell of rain on dry earth has a scientific name, and the atmosphere carries it. The scent that rises from dry soil after the first rain falls is called petrichor, a word coined in 1964 from the Greek words for stone and the fluid that flows in the veins of the gods. The smell is produced by a combination of sources. Certain bacteria in the soil, particularly actinomycetes, produce a compound called geosmin during dry periods, and when rain falls and disturbs the soil, this compound is released into the air and carried by the atmosphere. The human nose is extraordinarily sensitive to geosmin, able to detect it at concentrations of just a few parts per trillion. Another component of petrichor comes from oils released by certain plants during dry weather and absorbed into the soil, which are then volatilized by rain. The smell reaches the nose by the same mechanism as all other scents, carried in the air, dissolved in the moisture of the nasal passages, and detected by olfactory receptors. But the emotional response it produces in most people is immediate and often deep, triggering memories of childhood and specific places and times. The atmosphere carries not just weather and chemistry and light. It carries the invisible molecules that trigger memory and emotion, the smells that make a person stop in the middle of whatever they are doing and be briefly, completely somewhere else. The tropopause over a large thunderstorm is pushed upward by the force of the updraft beneath it. Thunderstorms are among the most powerful atmospheric engines on Earth. The largest, known as supercells, can sustain updrafts of over 200 kilometers per hour, carrying air from near the surface to the tropopause and beyond. When the updraft is intense enough, it can actually push the tropopause slightly upward, bulging the boundary between troposphere and stratosphere above the storm. These overshooting tops, as they are called, can carry water vapor and other tropospheric chemicals briefly into the stratosphere, injecting them into a region where they would otherwise rarely penetrate. They are visible in satellite imagery as bright white domes rising above the flat anvil-shaped tops of the largest storm systems, and they are one of the ways that chemistry and water from the lower atmosphere can enter the stratosphere and potentially influence the ozone layer far above. The thunderstorm is one of the atmosphere's most dramatic demonstrations of its own internal violence, a convective engine powered by the release of latent heat from condensing water vapor, capable of briefly reshaping the boundary between two of the atmosphere's distinct layers. The amount of oxygen in the atmosphere has remained remarkably stable for the past 300 million years. Today's atmosphere is approximately 21% oxygen, a proportion that has fluctuated over geological history, but has remained within a relatively narrow range since the end of the Carboniferous period. This stability is remarkable given that oxygen is chemically reactive and is continuously being consumed by combustion and respiration and continuously being produced by photosynthesis. The balance between these processes maintains the atmospheric oxygen concentration with a precision that is, on any human timescale, essentially perfect. The total amount of oxygen in the atmosphere represents hundreds of millions of years of photosynthetic production, minus everything consumed over that period by respiration, decay, and the oxidation of minerals. If photosynthesis were somehow to stop completely, all the oxygen in the atmosphere would be consumed by respiration and decay within a few million years. The oxygen you breathe is not an original property of Earth's atmosphere. It is a continuously renewed gift from the living world, maintained by the ongoing metabolism of plants, algae, and cyanobacteria in every sunlit place on the planet's surface and in its oceans. Certain high-altitude clouds can be seen glowing after sunset, lit by the sun from below the horizon. Under ordinary conditions, clouds stop receiving direct sunlight shortly after the sun sets and the sky darkens. But clouds at very high altitudes, particularly the thin cirrus at 10 to 12 kilometers and the remarkable noctilucent clouds near 85 kilometers, remain illuminated by the sun for much longer after sunset because they are high enough to still receive sunlight when the ground below is already in darkness. In the minutes and hours after a summer sunset, looking toward the western sky, it is sometimes possible to see high cirrus clouds still lit in gold and pink long after the sky has turned dark blue. These twilight clouds can be beautiful and can linger for up to an hour after sunset, depending on the cloud altitude and the time of year. The noctilucent clouds of the polar summer, glowing in their ghostly blue-silver in the north after midnight, are visible only because they are so extraordinarily high that the sun, far below the horizon, still reaches them. The atmosphere has different floors, and the sun sets at different times on each one. The sky you see after sunset is a gradient of illumination, darkening layer by layer from the ground up, the highest clouds the last to lose the light. Fog is a cloud that touches the ground. The distinction between fog and cloud is purely one of altitude. Fog forms by the same process as cloud, the cooling of moist air below its dew point until water vapor condenses into tiny liquid droplets. When this cooling occurs at ground level, it is fog. When it occurs above the ground, it is cloud. Radiation fog forms on clear, calm nights when the ground cools rapidly by radiating heat upward, chilling the air just above the surface below its dew point. Valley fog collects in low-lying areas where cold, dense air drains downhill and pools. Advection fog forms when warm, moist air moves over a cool surface. It's when warm ocean air moves over cold coastal water. Each type forms through the same basic physics, but in response to different sets of conditions. The famous fogs of San Francisco Bay, of London, of the Grand Banks off Newfoundland, are products of specific geographical and meteorological circumstances that concentrate the conditions for advection fog in particular places. Walking through fog is walking through a cloud, breathing in droplets so small they stay suspended in the air, each one a tiny sphere of liquid water waiting to evaporate when the temperature rises and the fog burns off in the morning sun. The atmosphere has helped scientists find planets around other stars. When a planet passes in front of its host star as seen from Earth, it blocks a tiny fraction of the star's light, producing a slight dimming that can be detected by sensitive telescopes. This is the transit method of exoplanet detection, and it has been used to discover thousands of planets. But if that planet has an atmosphere, the atmosphere can leave an additional signature. Light from the star that passes through the planet's atmosphere on its way to Earth will have certain wavelengths absorbed by the atmospheric gases, and by analyzing which wavelengths are missing, astronomers can infer what the atmosphere contains. This technique, called transmission spectroscopy, has been used to detect water vapor, carbon dioxide, methane, and other molecules in the atmospheres of planets orbiting other stars. In some cases, it has revealed atmospheres quite different from any in our solar system. The same physics that explains why the sky is blue above you, why the ozone layer absorbs ultraviolet light, and why greenhouse gases trap heat, is the physics that allows astronomers to read the atmospheric chemistry of planets orbiting stars dozens of light years away. Earth's atmosphere is not an isolated phenomenon. It is one example of a process that appears to operate around planets throughout the galaxy. And now, at last, the words slow down. You have traveled tonight through every layer of the atmosphere, from the breath in your lungs to the very edge of space, through the chemistry that makes the sky blue and the physics that makes rainbows appear, through the winds that carry Saharan dust to the Amazon and the atmospheric rivers that drench entire coastlines, through the lightning that strikes upward and the auroras that glow in silence above the poles, through the clouds named by a teenager in 1802 and the ice crystal halos that no one notices, through the thin ozone shield that made life on land possible, through the ancient air that early bacteria made breathable and the oxygen that plants renew with every sunrise, through the smell of rain on dry earth and the fog that is simply cloud touching the ground, through the atmospheres of distant worlds detected by the same physics that explains the blue of the sky above you. All of it is above you right now, the same sky, the same layers. The same extraordinary, fragile, ancient shell of air that has surrounded this planet through billions of years of change, doing its quiet work without pause and without thanks, connecting the surface to the sun and the ocean to the forest and the living world to the chemistry of a planet that has, so far, kept everything it needed to keep. You are inside it. You are made of it. Every breath you take is a small act of exchange with the atmosphere, a transaction that has been occurring billions of times a second in every living thing since the first cell breathed in the first ocean. There is nothing left to think about tonight, nothing left to understand. Just the slow rise and fall of your chest. The air moving in and out without any effort, without any decision, without any direction from you at all. The atmosphere doing its ancient, patient, unknowing work above you. Your body doing its ancient, patient, perfectly calibrated work within you. And the night doing what the night has always done, arriving without announcement, settling without sound, making everything quieter and darker and slower and softer until there is nothing left to do at all, but let go of the last thought and drift into the quiet that the atmosphere itself is resting in above you, above every city and every mountain and every ocean, above every sleeping person on this whole turning world. Sleep well. Good night.